Hi everybody and welcome. I'm so excited to record this video today because of some big news that hit the AI community. A few days back, DeepMind released a paper that it's probably the first glimpse at artificial general intelligence that I've ever seen. It's super promising. And if you're wondering what is artificial general intelligence, well, the idea basically is to build a multi-purpose agent that can act just like us, do a bunch of different tasks. Now, in this video, I'm going to break down that paper for you guys, and then I'm also going to discuss some of the implications of this new technology. Let's get started. The paper is titled A Generalist Agent. It's been published by several authors, by many researchers at DeepMind. Main author is Scott Reed. In a nutshell, these researchers built a single agent that's capable of handling hundreds of different tasks. And this should bring us back to a couple of concepts in artificial intelligence which are very important. On the one hand, we have artificial general intelligence. So this is basically the ultimate goal of artificial intelligence, if you will. The idea is to build an agent that's able to behave just like us humans, a central single agent that can work on most tasks out there. So this agent should be able to orientate itself within the world, to take decisions, to perhaps create art, to perhaps enjoy itself, right? But it turns out that building artificial general intelligence, it's a quite difficult endeavor. So rather than that, what researchers started to do was focusing on more specific tasks. So building an agent that can work well for particular problems in a particular domain. And that's what we call artificial narrow intelligence. And over the last 20, 30 years, we've been quite successful at creating effective artificial narrow intelligence agents. And we have so many examples right now, like speech processing systems, music emotion recognition systems, or image processing systems of all sorts and kinds. But all of these systems or agents work well with a particular task in a particular domain. Now, what these researchers at DeepMind have tried to do is to create a system that could resemble a little bit more or get closer to artificial general intelligence rather than artificial narrow intelligence. And indeed, they started with an interesting hypothesis here. So that, first of all, it is possible to train a single agent capable of carrying out a large number of tasks in different domains. And now there's a sort of extension to that hypothesis that, builds on top of this statement, which is this agent can be adapted with little extra effort to succeed at other tasks as well. And if you think about it, if these two hypotheses are correct, then this could be the sort of basic recipe that we use to get to artificial general intelligence, which is basically being able at carrying out many tasks in many different domains. But now, all of the paper is a sort of investigation into this hypothesis. So I suggest we start looking at it so that we can see whether these two hypotheses are actually possible or at least plausible. Okay, so now let's take a look at how the researchers approached artificial general intelligence. Well, of course, they don't claim that they're working towards artificial general intelligence or that they've reached that in this one paper. But I'd like to think that this is the first step to approach AGI. So there you have like the title of this slide. So what did they do? Well, they basically used the most advanced language model that we have right now. So basically they used transformers, or they actually used a transformer model with these characteristics. So you have a single architecture, that's a transformer architecture, that's able to work on multiple tasks, more than 600 tasks in different categories. And indeed, the model is capable of handling different type of data in different modes. It can handle text data, it can handle image data, it can also process button presses. And why button presses? Well, because some of these tasks had to do with Atari games, and DeepMind is quite famous for its reinforcement learning agents capable of achieving superhuman results at Atari games. And the other aspect is that this system is also able to work in different environments. So it handles multi-embodiment, because as I said, some of these tasks are within a game, really, so an Atari game or a simulation of an Atari game. Other tasks have an impact in the real world because this model is able to give directions to a robot arm to solve certain problems, like stacking things, or like piling up things like in a certain manner, or pushing blocks. Now, the interesting thing is that, as I said, here we have a single multi-purpose architecture that share the same weights for all the different tasks. So as you can see, this is an initial step probably towards artificial general intelligence intended as having a single model that can work on many different tasks that are kind of different among themselves. Okay, so here you have a nice representation of this agent. Obviously, this figure comes directly from the paper. First of all, the agent is called Gato, which in Spanish is the term for cat. So we have a cat agent. And as you can see here, Gato is able to work on many different tasks. It can work as a rudimentary chatbot. So you can ask things to Gato, and hopefully Gato will answer like your questions in a reasonably good manner. It's able to provide instructions to a robot arm. It's able to provide captions to certain images, and it can also work or try to solve Atari games like this. So as you see, a lot of different types of inputs in and a lot of different outputs and tasks that Gato can actually handle. Now, a question that I think it's important to ask is, why should we focus on a single architecture for many tasks rather than having many different architectures? Well, having many different architectures is the way that we usually work in artificial intelligence right now. So it's the artificial narrow intelligence approach. But there are obviously benefits to having a single multi-purpose architecture. First of all, you don't need to craft domain-specific policy models. And that's obvious because you have a single architecture that can work on many different tasks, and we don't have to think too much about a particular task and build and train the model on that particular task only. We can have a single architecture that is able to handle multiple tasks and learn multiple policies for different tasks. And then it can also help us to increase the amount and diversity of training data. Of course, if we have many tasks, this means that we're going to have different data sets with different modalities, with different shapes, formats, if you will, and this is going to basically increase, by definition, the amount of diversity that we have in the training data, and that this hopefully is going to have a good impact across different tasks. So yeah, these are two interesting benefits that we would get by having a single architecture. Now, let's take a look at the actual datasets that the researchers have used for their experiments with Gato. So we have datasets that are like in 3D vision and navigation, because Gato is able to navigate simulated 3D spaces. We have datasets for Atari games. Then we have datasets for planning being a subfield of artificial intelligence, mainly stuff like putting boxes in certain orders, and so you have to push them around, following a certain sequence of instructions so that you arrive at a final setting. So some things also in the real world, like robo-arm, so like for example, like stacking or piling up like different things in the real world. But there are also datasets in different modalities, like text, for example. So there's also like something else like vision and a language datasets, and these are used for captioning. So you have an image and you want to say, okay, so here I have a dog barking at a person, for example, right? And there are also other datasets for question answer. This is like typical datasets that you would use for training chatbots. Here in this table, you have a breakdown of all the different datasets used and the sort of like weight that they had within like the overall training. Cool. Okay, so now there's a big problem, I believe, which is we have a lot of datasets in different categories, in different domains, with different formats. So how can we train a single model on such heterogeneous data? This data is quite different, it's quite heterogeneous. So how can we take all of this data and put it in a format that's understandable by our model? Okay, and here comes tokenization. The idea is that we take all the different data and we tokenize it and we put it in a sequence of tokens. And these tokens now look more or less the same. So we have some procedures for taking all of this very heterogeneous data and convert it to some tokens that the model can actually understand. And these tokens that we get in the end will be ordered in a sequence because, if you remember, we are dealing with a transformer. So we need to have data that in a sense resembles language data, right? Where you have a lot of tokens. If you will, it's basically like a time series or a sequence of tokens. Now, let's take a quick look at some strategies that have been used for tokenization. And here I'm just referring directly to the paper. The interesting thing here is that they use different tokenization strategies depending on the different data that they have. Let's take, for example, text data, so language related data. And so this text data is encoded via sentence piece. And what's this thing? Well, this is a model that does tokenization for text data. And so that at the end, they have 32,000 subwords into an integer range from 0 to 32,000 excluded, right? And so this is a way of like tokenizing the text data that they get. But for other type of data, like for example, for images, they do something different. Or same thing for discrete values, like for example, the Atari button presses, which are actually flattened into sequences of integers, right? But here, the whole point is taking all of this quite different data and put it into a sequence, right? Now, let's go back here. Tokenization is not the end of the data preparation process. It's actually the first step. Now, we also have another couple of steps. So after we've tokenized all of these different data sources, we have to order them into a sequence that makes sense. And then we have to embed them. So, and how does that happen? Well, once again, if we refer back to the paper, you can see that they use different canonical sequence ordering techniques depending on the type of data that they want to, or type of tokens at this point that they want to order. Yeah, for text tokens, for example, they just use the order of the row input text. Well, this is like obviously like quite natural because text come already as a sequence to start with. But for image patch tokens, and that's like how they actually tokenize images, they just like create some sort of like patch tokens. For that, they take a raster order, and for all the different tensors, they just like go for row major order, which basically means that they just like go through like a row, then they go back to the start of the next row, and they flatten all of that matrix in that way. But yeah, then the next step, the third step that we've seen in data preparation is embedding. So they take the input tokens that now are ordered into sequences and they embed them. And they embed them using a parameterized embedding function. And this is like sort of like very simplified function at a very high level, where theta are the different parameters of this embedding function. Once again, they use a different embedding techniques depending on the type of data that they're dealing with. In the case of text data, discrete and continuous value observations or action, so what they do is they embed them with a lookup table and they embed them into a learned vector embedding space. But for example, in the case of image patches, what they do is they sort of create an embedding using a single ResNet block. So they start with this image patches and then they get back a vector. That's your vector embedding for that particular patch. Okay, so now at this point, we know how the data is sort of made homogeneous so that the model can understand it, even if it comes from very different sources, which can have different modalities, as we said. Okay, let's take a look at the architecture. So this is nothing fancy at all. This is some basic transformer architecture, and here we have some parameters. Like the most important, like interesting ones are the number of parameters, and here you'll see that we have 1.2 billion parameters, more or less. If you think about it, this is not really a super large network. Think of GPT-3, for example, where you have 175 billion parameters. It's 2 order of magnitudes more than Gato. And you may ask, well, why do they choose to have such a small parameter size? Well, because they want to do things in real time. So they want, for example, to be able to send instructions to a robo arm in real time. So they have to process all the incoming information, sample the action that robo arm should take, and then send it. So if the parameter size is too large, then that's not going to happen. So they basically built the model in such a way that it can work in a real time, given the hardware constraints that we have at this point. Cool. So for Gato here, for this version of Gato with 1.2 billion parameters, they have 24 transformer blocks and they have 16 attention heads. Now they also worked with smaller models. You can see here one at 350 plus million parameters and one at 80 million parameters. And this have been used for ablation studies. We'll cover some of that later. Okay, so now we know about the model architecture and the rationale behind the number of parameters that we have. Let's take a look at training. So here they produce this very nice figure. So the first part we've seen already. So what they do is they take all of this different data, like for example, Atari, images, text, images or images and questions, and they just convert all of that into a batched input. So this is a sequence of tokens that have been, of course, tokenized, ordered, and embedded. Okay, and they pass that to Gato. They model the data in an auto-regressive manner. What does that mean? It means that the input can also become the output or the target, right? So it's a little bit like what you would do in a simpler model like an LSTM when you want to predict or forecast time series, right? So you have many time steps, and then the certain time steps that initially are targets go back and become inputs, right? So you have this sort of auto-regressive treatment. So all of this to say that they can use some of these tokens and sequences initially as inputs and then shift them and use them as targets as well. Now, the most interesting part probably of this training process is the loss function that they use. It's this one here that, of course, takes into consideration the target sequences, and it's a function of theta, that these are the parameters of the embedded tokens, and b, or uppercase B, and this represents the current batched input. Okay, so now let's take a look at the loss that they use, because it's quite interesting. So first of all, here you can see that they actually model the probability of a sequence of tokens S1 to SL using here the chain rule of probability, and basically they sum over a bunch of conditional probabilities, right? And they sum that from with L starting from 1 to capital L. Remember, like this L index is just the index of the tokens that we have in the overall sequence here. And so this is like the probability of having a certain sequence with tokens from 1 to uppercase L. And this is something that they use directly in the loss. So this is the loss. So as we said already, this depends on theta, so the parameters of the embeddings that we have. And it also depends on capital B, which is the batched input. Now, you may recognize that we're using this chain rule of probability in here somewhere, and it's this part. The two parts obviously like are the same. There are still a couple of elements that we haven't covered yet. So one being the this other sum here over this index lowercase b, and then we have this other function called m. Now let's take a look at both of them. The first one is the sum. So b, or lowercase b, is the index of the training batch. Given we are training in different batches, of course, for this loss, we have to sum over all the different batches. So from the first batch all the way up to the current batch, the last batch. But now there's still one piece missing to this loss, which is the M function, which is a masking function that depends on B, so the current, of course, like training batch, as well as T being a time step within the sequence, so being a particular token. So why do we want to use masking? Well, we want to use masking because we want to use only certain inputs and train with certain particular inputs, but not on others. Indeed, this masking function is equal to 1 if the token at index t is of type text or agent action. It's 0 otherwise. In other words, if a token is of type image or if it's an observation. In the case of input that comes from originally from an image or an observation, we want just like to make the contribution of these inputs completely null, like completely ignore that input. Now you may be wondering, but what are like actions and observations? Well, the idea is that like an agent, of course, like for example, an agent that can play an Atari game can take some actions, like for example, pressing a button, and it also sees some observation. In other words, like it sees the environment, for example, of the game, of a real world situation. If you have a robot that has to navigate a 3D world, so for example, like coordinates or like obstacles that you might encounter or something like that. So yeah, we want to ignore observations and image type data from contributing to the loss and therefore contributing to the training of the model. Cool. Okay, so this is the interesting loss that they are using for training the model. Now, you may be wondering, we are dealing with a bunch of different tasks here, right? So some of these are, we saw, like image captioning. Something else could be like 3D navigation, Atari games. So how does the model recognize all of these different things, all of these different tasks, and decides how to respond to that? Different tasks can have same embodiments. In other words, they are within the same environment. They may have same observations or tokens that are very similar because they represent the same observations and same actions as well. Take Atari games, for example. You can have like similar actions, which is like press button A, for example. So how do we let the agent know that we want an answer, like a prediction for a particular task? Well, there are different strategies to go about this, but one could be just to hot encode, for example, all of these different tasks, and when you pass a sequence, you just like tell the agent, hey, this is Atari game 1 or this is image captioning. But they decided to use another approach. So they use a prompt sequence for conditioning the model. So what's this prompt sequence? Well, it's a sequence that comes directly from the agent, and it's indeed a sequence that has been generated by the agent on the very same task, and that is prepended to the batched sequence that we pass to the model. In other words, we're basically telling the model indirectly that they are working on a certain task because we are passing the model a small part of a sequence that is the output of the model on that very same task. In this way, we are conditioning the model. And you may be wondering, but why are researchers using such like a weird approach? Well, The hope is that then, if the model is general enough, you could change the prompt sequence with a prompt sequence that comes from a task that the model has never seen, and hopefully the model will understand, will codify like that prompt sequence and respond with actions that make sense for that task that the model has never seen before. Now, stay tuned to know whether like that technique functions, but I believe like this was the sort of like reasoning behind this approach rather than a simple one hot encoded approach, which probably would be just easier. Right. Okay, so now we know also how the model recognizes which tasks it's working on in a current like inference process. And talking about inference, let's take a look at how inference work, or in other words, how we can deploy Gato as a policy that can take action within the world given certain observations. Okay, so we start with a prompt sequence, and we pass this prompt sequence directly to Gato. The next step is to get observations from the environment, and this could be different things, right? It could be, for example, an image for captioning. It could be, I don't know, like some pixel coordinates, like for Atari games. The observations from the environment are tokenized, and they are appended to a sequence. Of course, they are tokenized, they are sequenced, and then they are parameterized. Then inference actually happens, so we can sample a tokenized action. But of course, the action that we are getting out of Gato is not in a form that we can directly pass to the original environment, of course, because it's a tokenized action. So we need a sort of inverted procedure to go from the tokenized action to the original action, to a format that the environment can actually understand. In other words, what we do is we invert the tokenized action. Now we have an action that can be understood by the environment, and indeed we pass it to the environment and we apply, therefore, the action to the environment. And the environment will obviously change its state based on this action, and it will just send back new observations. And indeed here we just repeat, we go back and we get a new batch of observations, and we just loop through this sequence or like this different procedures once again. Cool. Now, one thing to understand here is that Gato sees all previous actions plus observations. In other words, it has a memory, but unfortunately the memory can't be infinite. Rather, it has a particular context window, and the context window that they apply is 1024 tokens. Cool. Now, here we have the most interesting part of this paper, right? So it's all well and good. This is a really good idea, but does it actually work? So let's take a look at this. Now, it turns out that for 450 tasks out of 604 tasks that Gato can sort of like carry out, its score, it's over 50% of the expert score. Now, what's the expert score? Well, the expert score is sort of like a threshold for a certain task that's provided by experts for that particular task. For example, it could be like Atari players who are really good at what they do. They're experts, and so they set a certain threshold of quality or performance for that particular game. So in this case, we see that the model performs reasonably well, so above 50% of expert score in the majority of all of its tasks, which is quite something if you think about it. Now, in particular for the Atari dataset, which is the one that has all the Atari games, the model is able to perform at average or superhuman performance for 24 games. The state of the art with reinforcement learning is 44 games. So yeah, this is quite impressive if you think about it, because of course, I mean, the Gato is not as good as the narrow intelligent agent, reinforcement learning agent that was trained only on Atari games, but it's actually performing reasonably well. Now, also to give you another example, and you can find more information about this evaluation in the paper itself, but on Baby AI, which is sort of language dataset, researchers report that Gato has 80% of expert score for almost all levels, which is quite impressive. And for the most difficult level, which is called boss level, it performs at 75% expert score, where the state of the art is 90%. Now, think about this. The state of the art model was trained only on this particular boss level task with millions of examples. Gato didn't have millions of examples only on boss level, and it's actually addressing more than 600 tasks, which is mind-blowing if you think about it. And then researchers found out that Gato is also able to work reasonably well as a chatbot and for captioning images. So here I just want to give you a few examples. So we have this image, and Gato came up with these three captions. A baseball player pitching a ball on top of a baseball field, which makes sense. A man throwing a baseball at a pitcher on a baseball field, or a baseball player at bat and a catcher in the dirt during a baseball game. Yeah, this is not accurate, but you see like 2 out of 3, the first two captions were actually quite good. So let's take a look at another example. So first caption, a couple of people are out in the ocean. Well, that's not perfect, but it kind of makes sense. But the other two I think like are quite good. So a surfer riding a wave in the ocean, and a surfer with a wetsuit riding a wave, which is quite impressive. And here we have an example of a very simple conversation. So Gato, please explain the basics of black holes to me. So I guess I'm trying to answer this simple question. What's a black hole? Indeed, please go ahead. Black holes usually occur when a star dies and implodes in a runaway reaction. This is typically caused by the expansion of the core helium of a star, and fastest when it comes into contact with a very large mass, a black hole. Yeah, so this is like, I mean, an interesting answer. And some of these conversations make more sense than others. Once again, I want to refer you back to the actual paper that you can find obviously in the description box below to get like a better taste of the strengths and weaknesses of Gato when it comes time to these tasks that are easier sort of like to qualitatively evaluate just by looking at them. Okay. Then researchers did also a very interesting thing, which was a scale analysis. Do you remember that they also shared information about 3 models? So one with 79 million parameters, one with plus than 350 million, and one with 1.2 billion. As you can see, the more parameters the model has, and the better the overall performance. And here, like the performance is a function of the number of tokens processed. So more tokens they process and the better they perform. And here on the y-axis, you have this mean normalized score. That's a super aggregate score that gives like the performance of these models across all the different tasks, right? And as you can see, like the more parameters you have and the better the relative model performs, which is quite interesting because this opens possibilities, which is what happens, for example, if we continue adding more and more parameters. Probably the model will continue improving. Let's take a look at another experiment that researchers tried out. The goal of this was extending the model to unseen tasks. And here they used prompt sequences. So they took prompt sequences of completely unseen tasks and they used them to condition Gato in the hope that the model would create actions which could potentially make sense for these initial prompt sequences. But unfortunately, this didn't work, and probably didn't work because the problem space is very large and these sequences can be very, very long and very difficult to sort of like be codified and understood by the model. So what they did instead was trying to fine-tune the model, because indeed they found out that they have to fine-tune, so they have to train the model with some samples of the additional tasks or the completely unseen tasks in order for the model to work. So what they tried to do was fine-tune the models with a little sample data. In other words, they were trying something like few shot learning, just like a few samples to expand, generalize the model to new tasks. And in their experiments, they tried to fine-tune on different variants of the model trained with different data. They had 4 different types of models. So one which was trained directly like from scratch, only with the data for the new task. Then they trained or they fine-tuned a model that was trained on no control data. So this is data that has nothing to do with the with tasks of the same domain of the new unseen task, right? So say, for example, they want to extend the model to a new Atari game, then they would start from a model that has never seen any Atari related data, so no control data. So then they try to do the fine-tuning on models which were trained only on the same type of data. So in the case of Atari, a new Atari game, so the original model was trained only on other Atari games. And finally, they tried to do the fine-tuning on the model trained on all data. Let's take a look at the results. And as you can see, here you have 4 different tasks. So Atari boxing, for example, which I guess it's a game, an Atari game, card pull, swing up, and a bunch of others. All in all, you can see that the models that were fine-tuned starting from the all data model were the ones that performed usually the best. The second best was starting from models trained on same domain only data. And then we have no control data, and finally we have like starting from scratch. So all in all, I think it was quite effective, this idea of extending the capabilities of Gato to other unseen tasks. But in order to do that, you have to do some fine-tuning. Let's just like try to summarize everything that we've sort of learned so far and focus on the main key discoveries. So first of all, generalist agents can perform reasonably well on many tasks, many embodiments, and many modalities. So this is something incredible. This is something so cool that goes almost against everything that I've learned so far about AI. Because, I mean, the whole point of AI over the last few years has been just focus on a problem and try to solve that one. This approach just goes against all of that, showing that it is indeed possible to have generalist agents that can work not just on different tasks, but on data that's completely different in nature, coming from different modalities and acting on different environments within a computer simulation, within the real world, sort of like influencing the movement of a robot arm, for example. It's quite mind-blowing. Then generalist agents have the potential to learn new tasks with few data points. Again, this is quite impressive because starting from a good, solid model trained on many tasks, it is possible to generalize the tasks that this model can carry out by using some simple, relatively simple few-shot learning. Then this final point is probably the most important in relation with our sort of search for artificial general intelligence. The performance across all tasks can increase with scale in parameters. This opens up incredible possibilities for the future. Indeed, as the researchers say in their conclusions, by scaling up the number of parameters, the computation and the hardware, we can build a general purpose agent. And when you arrive at a point where you have many tasks in many different domains, well, it's a matter of philosophical question, but at some point you have to declare that you have reached artificial general intelligence. So yeah, I'm really impressed with this work, and after I've read through it, after I've seen the evaluation and the conclusions, I was sort of relentlessly asking myself, are we really witnessing the dawn of artificial general intelligence here? Of course, this system, Gato, is by no means an AGI agent. No, it's not. But is it the first step in that direction? I don't know. What do you guys think? Probably yes, I would say. But yeah, let me know. Let me know in the comments below, because I'm curious to hear what you guys think about this. Now, I think when you are at such a massive revolution, potentially, you have to think about ethical implications. And that's because these generalist agents can act in the real world in so many different ways. They're not just limited to a particular narrow task. They can do so many things. They can have so much influence and impact on the real world, and this brings ethical implications. We have to really think about most of these things. One of the risks that the researchers highlight, and I think this is really can be a danger, is this. So you have an agent that can work on many different tasks. Now imagine that you embody this agent within a robo, for example. Give that robo a human shape. Now you are anthropomorphizing that robo, and with that probably starts to grow trust, blind trust, because this robo resembles me quite a lot because it can do many tasks that I can do. So it can trust this robo. But I mean, blind trust in a generalist agent could be really risky, because the way they operate is very different from the way we operate. We have, or most humans have at least, some sort of moral compass. But these agents don't have that. Or even if we train that moral compass, it could be trained on very bad data, and they may respond in ways that we don't want them to respond. So we can't just blindly trust their actions and their decisions in a sense. All of those decisions have to be vetted at a certain point. And this risk is also connected with another point, which is there may be unexpected emergent capabilities. So for Gato only, for example, the model has been trained on so many datasets, so many data points that it's basically impossible to just like vet all of this data and to understand all of the possible implications and decisions that Gato could take in a certain situation. Now imagine if you had a model that was even more powerful than Gato. These models could potentially showcase emergent capabilities that were completely unexpected. So in order to avoid all of these problems, we would have to vet the dataset that we use for training, test massively these models in order to understand most, at least, of the possible edge cases that they can cover. But still, there's a risk of unexpected emergent capabilities just by how we've trained these models and just by their nature of multipurpose agents. Then there's also a risk of passing certain knowledge from a domain to another domain, and by doing so endangering humans potentially. Researchers in the paper mentioned a very interesting example. The model is capable of aggressive behavior within like fighting games, Atari fighting games. Now imagine if you were to use this initial knowledge and transfer it within the real world for a real world robo. So that could be extremely dangerous. Finally, I think one of the major risks out there is the abuse of such powerful agents for bad goals. For example, using these powerful models for military goals. And it's not just a risk, this potentially can be a reality, because we've seen time and again that great inventions, great technological advancements have been used for really bad goals in a military setting. So I think that as a community here, we shouldn't just be super happy about these advancements, but we should also start a discussion. Because as we've seen for Gato, like this technology is advancing at a very, very fast pace. And with that come, I believe, very deep questions, ethical questions that we have to address. And as experts of this field, we should be, I believe, a beacon. We should just start saying, hey guys, we have to think about what we are building, and we have to let society know about the possible pros and cons that come from this technology. At the end of the day, I think it's a matter of weighing the benefits, the cost and the benefits, and understanding whether it really makes sense to push us ahead and really arrive potentially one day at artificial general intelligence, because that will come with a lot of risk and danger. So what do you guys think? I really don't have an answer here, and this to me is still really, really new. And before it came out, I wasn't really thinking about AGI, because I thought, well, this is going to be something, I don't know, like down the line, 20 years, 50 years, who knows? But I feel that we are getting just a little bit closer. So yeah, please let me know in the comment section below. Cool. So this was a great paper by DeepMind. I really hope you enjoyed this video that you've learned a lot. If you want to continue the discussion about the technical details or the ethical implications, I encourage you to join the Sound of AI Slack community, which is the community connected to the Sound of AI YouTube channel. There we are more than 5,000 people all interested in AI, in particular to AI music and AI audio. That's all for today. Once again, I hope you enjoyed the video and I'll see you next time. Take care.